Alright, this is part 2 of Basics of Logic Design, Appendix B. So I broke it into two major parts, the first one being about 40 minutes long. This one will be about equal amount of time, and it goes more in depth in the topics we touched on, such as in last lesson we talked about a few definitions of gates, logical 1 or 0, what a logical block or basic building block is, and especially combinational versus sequential, right? Which one is memory? So that's sequential or stateful logic. We talked about truth tables and how we can create Boolean logic and convert it into using the identities and operations and basic circuits. We can convert this into building block circuits, essentially. And we talked about how we get to each of these and their decoders and muxes, and basically the and or planes that programmable logic arrays allow us to build based on truth tables. We also talked about timing with clocks and rising and falling edge briefly, and a few other things. So we're going to go more in depth into each of these areas. So we left off, and one of the areas we didn't talk about is don't cares. So when you're building, so we're going to hop right in. So when you're building a truth table, this assumes that you care about every state. And we talked about how to get the Boolean arithmetic for case D assertions, case E assertions, the ones, and case F assertions. And then how to build that into a basic circuit. But what about if you don't care? What if there's certain states that occur, certain combinations that occur, permutation that it doesn't matter. It just doesn't matter. Well, the highly technical name is don't care. And what you do essentially is you mark the input or output as a don't care. And it's highly technical. If it's a input, that doesn't matter, or an output, that doesn't matter. If it's input, it's input don't care. If it's an output don't care. So really not too technical here. So the book does a pretty good job talking about this. It shows 696 on mine, but basically it shows the same table we had been working through in the previous presentation. And it said, okay, this, as I introduced, assumes we care about every one of these permutations. Well, what if in actuality we put x's, we don't care about the state of f if D and E are 1. Okay, we just don't care. You can see here D is a 1, E is a 0, so we care about f. D is a 0, E is a 1, so we care about f. Oh, if D and E are both 1, then we don't care about f. So then we can mark all of these as don't care. Well, then we can also look at our inputs, and we can mark out, and this is based on the system you're designing for. So this is just a purely a hypothetical example to give here. So then you can reduce the don't cares on the input side. Well, then you can simplify your truth table to all the states that actually matter to you, that capture the permutation you're interested in, with all the extra don't cares removed. For example, they said that if they have a 1 in A, then they don't care about B and C. So that's this state right here. And so that's all combined as one state. Or for example, if you have a 1 and 1 in B and C, then they don't care about A. So that means we can simplify several cases. We can take this case and put it down. And for example, if you have, I guess the easier one to describe for presentation purposes is all these don't care output states, where if you have a 1 in D and E, you don't care about the last one. Well, that removes, we've compressed 1, 2, 3, 4, 5, 6 cases down to 1, 2, 3 cases. So think about how much less Boolean arithmetic that is, and therefore how much less or better optimized circuitry, because you can reduce in your AND plane and your OR plane a significant number of circuits. So that's what don't cares is about. I said we talked about it in the previous, so we talked about it. And there are some proven processes to do that the book talks about here on how to determine and optimize don't cares. Alright, now let's get into, so we've kind of beat this table to death. It was hypothetical. Let's put it into a real example. For example, MIPS that we've been going through the whole semester. So MIPS, as you know, has the different types of instructions, R, I, J type, but let's focus on the R type, right? The R type breaks up, and maybe it's been a while, so I threw this in the slideshow so you'd have it. The R type breaks up each of the 32 bits of the instruction into different parts, as it states here, so that's easy for use. One of them we've talked about previously, and it mentions in chapter 4, is the opcode. We've talked about that a lot. And the function. And the opcode and function bits interact with each other. Well, that's what this is. That's what this example we've been talking through. That's why the opcode and the function codes exist in MIPS, is for this reason, right? If this is our MIPS data path, right, for a single control unit with an ALU, okay, when we load a single instruction into memory, right, 32 bits, 0 to 31, right, some of those bits are going to be the opcode, okay, and some of them are going to be the function portion. Well, our control unit, which is just essentially a decoder here, determines the control path, and for example, one of the outputs of that is the register destination. So whether it's RD, okay, or if it's RT, okay, so which of these two register destinations. So based on the opcode right here, so 6 positions, 0 through 5, and the function value, which we don't list out here, 0 to 5, right, we create a table, just like a truth table, just like we've been going over. So we can just convert this into Boolean arithmetic, which we do right here, right? So the register destination, based on our truth table, and we do care about every one of these, there's no elimination here of don't cares, is going to basically be not op5 and not op4 and op3, not op2 and not op1. Well, that's both these cases which apply to the add immediate and add immediate on signed. So this is just to demonstrate the so what factor. Here's where all of this comes into play. And you can see MIPS was designed with opcodes and the function code to go through its logic, and they designed it just the way we've been talking about. And this is the simplified circuit and design here with the inversions on op5, 4, 2, and 1. Just some symbology I didn't talk about last time. Basically, when you see the slash, that represents a bus. So this is the compressed version, because it's a lot more work to write out for a 32-bit wide multiplexer, for example. Every bit and its carry what comes out of that. So we simplify it with this picture. Not going to talk about parity logic. Talked a little bit of hardware last time. I'm not going to talk more about that. I am going to talk a little bit about blocking and unblocking. Remember, we've talked about combinational and sequential logic, where combinational logic is always available and sequential is state-based, so, or memory. Well, in some of these hardware description languages like VHDL and Verilog, they created a syntax for this, where blocking assignment uses this symbol and non-blocking assignment uses this symbol. Well, what does that mean? When you write the code in VHDL or Verilog, there's some additional constraints like an @always that you have to use. Anyways, won't get into that here. What that allows you to do is some values are basically combinational logic, and so you're going to use these symbols because it's always available. Whereas some logic that you put together is going to be sequential or data based. So it depends on the previous state and the current clock cycle. So you use this assignment statement. So how does that impact? Well, it just us for consideration, right, when you've got these functionalities like a sign extender, a register file, and an ALU, and a shift left, what is it, blocking or non-blocking? Well, this is semantics, but as I showed here in the previous slide, blocking being clock cycle dependent, non-blocking being always available. So you can think of this as memory required or a clock cycle required, non-clock cycle required. So this makes sense to me because a shift left 2, as we showed in chapter 4, it's just moving, reassigning the wires. It's just wires, and so there's no data store. The same with the sign extender. There's really no data storage occurring. But ALU may have a previous state, and register file, definitely register file we're going to talk about in a little bit, just being a register. There's data being saved in there. So there's sequential logic in these, whereas these have mostly combinational. It's not even really combinational, it's very simple logic. Talked about this last time, talked about a 1-bit adder truth table last time, talked about negative numbers last time. We talked about stacking 1-bit adders last time to create a 32-bit adder. And we talked about why we do 2's complement. What we didn't talk about in full detail is the 32-bit ALU. So the 32-bit ALU, you can see here the one thing we didn't talk about is SLT. So the set less than. So because there's additional logic required for set less than, there's kind of a jump here in the slideshow. You can see we went through the carries in and out, and we talked about that a little bit. We're going to talk more about it here in a second. What we didn't talk about is the set less than. So you can see we just kind of jump here. Well, when we're doing ALU operations, right? What are the commands we usually deal with? Well, we're dealing with and, or, addition, right? We already talked about inversion, so we get subtraction out of that. Inverting either A or B and doing addition. And then we can get the carry out of that based on what we've talked about so far. But what about if we want to check if A is less than B, or B is greater than A? Or what if we want to branch equal, check if they're equal? So we need additional logic for that. So one of the ways we do that is with a SLT logic. And basically in each adder we add additional logic to check if B is greater than A. Okay, and for each bit. And then the last one finally sends out the set for this. See how it's A31 and B31, so this is the most significant bit. This is the 31st bit, 0 to 31. So this will finally determine if there's essentially overflow, right? Which can tell you if B is greater than A or if B is less than A. And likewise, now that we have that additional logic added in here, what we can do is then we can also add logic to see if they're equal to 0. In other words, if there's no carry and A minus B equals 0, so the two values are equal. The book talks about this. I'm going to pull it up. It does a fairly good job. We'll pick it up here. Right here. So at page 711, you can see we have the logic we talked about last time for what kind of operation we want. An AND operation going through this adder. This is an adder. It's not complete. And well, it's hybriding into an ALU, right? So we're starting with an adder and slowly building it into an ALU, right? So we have A and B as our inputs. We talked about this last time. So we have the ability to invert A or B, okay? We can perform an AND operation, an OR operation. We can also perform addition, right? So depending on, this is your select, right? Well, like I said, we want to take that a step further, right? We want to deal with the SLT, okay? Well, how we can do that is just like I talked about, A minus B, which essentially is just A plus the invert of B. And what that looks like in implementation in logic is we have to do pardon me, a little more work. They show an intermediate to arrive there, and this is how we arrive there. So as I showed in the slideshow, we have to in each adder check that if there's a set less than bit for every single addition. And this is how it's implemented in a MIPS example, is for every single, and this is for a single bit, so A1 or 0, B1 or 0, right? Single bit, what we have to do is we have to create a separate value, a separate data path, right, for set, right? And then we have to add logic for overflow detection. So it adds a little bit more overhead than planned, and then finally we add an additional selection to see if it's less than, right? And this is kind of confusing the way they throw this way out here, but again, 0 is and, 1 is or, 2 is addition, 3 is set less than. All right, and then finally, and here's what you see on the slideshow, finally kind of putting this all together to deal with A equals B, we just do A minus B. So we get the final logic here, which they recommend just ORing all of it. So one way we can see if it's equal to 0 is just OR every result, the sum of every single bit adder. And if any of them are a 1, then we know A didn't equal B because there was some value, whether it was addition or subtraction or performing, it doesn't matter, there was some remainder. So from one of these single bit adders, and so when we OR all that, if there's any 1, then they weren't equal to each other, and so and it inverts it, so you didn't have A equals B. But if every one of these is 0 and you OR all of that, you'll get 0 out of it and invert that. Therefore it is true that they're equal to each other. When A minus B equals 0, the OR gate, they all pass through as zeros, invert it, and the state is true as they're equal to each other. Now what we've done is we have created, by combining all these basic single bit adders with the additional logic we've talked about right here, we've created essentially the MIPS ALU, because we have AND operation, OR operation, addition or subtraction using the invert. We have set less than and overflow, and it doesn't show it here, but we can also set, we could do selection for, which check if they're equal, branch equal, okay? So that's just the ALU portion. Alright, so that went into more depth on that. So that's all of that, right? All of this logic right here, right, is simplified by this symbol, ALU. Alright, single 32-bit input, A and B, whether there's a carry, 0, or the result, and if there's 0, the result and overflow. And now we've seen how all of that comes together. This is how, I touched on it briefly last time, but this is how you would implement this in Verilog and VHDL. This is the additional statements I said that we would need an at always, so that these values are always available. So this is cool, because what this means is there's, well, for the purpose of implementation, there's no propagation delay, so this isn't sequential logic, it's all combinational. So putting this always at means anytime this input changes, or this input changes, it immediately reevaluates it, okay, into one of these cases. So it's not like what you might be used to in C or Java or Python. I'm trying not to date this lecture, but whatever the current programming language of choice is, don't read this like a standard case statement that it's going through each one of these and checking them. No, it creates a separate simultaneous operation for every one of these, and so whatever case it is, if one of these has occurred, it automatically goes to that case and then performs whatever logic needs to be accomplished immediately based on the new value. So that's we can talk another time. If any of you are interested, you can talk to me about programming FPGAs and other programmable logic devices as an aside. So this is kind of what I just talked about. Software is sequential, inherently not parallel, but hardware can be constructed to be truly parallel. For example, this MIPS ALU encoded in Verilog. This is all this is built out, for lack of better words, simultaneous. So even though it's written like this, because this always at, and you can see this type of assign statement, these values are immediately available. So we can add sufficient hardware to make operations parallel, but design is one challenge in software, right? How do we express this so it truly acts parallel or behaves parallel? The other problem is, well, if we just keep adding hardware to make everything parallel, there's obviously a limit, an upper constraint to that. How much hardware, what's the cost, how large, and we talked about heat loading earlier. Okay, now let's transition and talk about arithmetic with a standard carry. So we talked about setting up a carry which is called a ripple addition with a single bit adder, and each single bit adder just flows the carry into the next. Okay, well, this clearly is not parallel, for example, in design, the way this is designed. But there is another way to design this based on Boolean arithmetic, so that you can add and deal with the carries and what are called propagates in a separate logic circuit, and do those in parallel with the addition of A and B. What that looks like is here. So you can put together what's called a propagate term and a generate term, and the book spends a lot of time on this. Feel free to dig into it. And you can see in 4-bit blocks. So we have 1, 2, 3, 4 bits here of A and B being added, and their literal values, right? And there's 4 of these, right? So 4, 8, 12, 16 for 16 bits, right? 2 of these to do 32-bit ALU. Well, yeah. Anyways, it's not truly ALU, but anyways, as an adder, right? And this is not a ripple. This is what's called a carry look-ahead unit. So instead of rippling, instead of A0, A1, A0, B0, A1, B1, and sequentially going down every one of them, right? So we create some propagation there, right? Instead, this is simultaneous because A0, B0 are combined, A1, B1 are combined, and so on, all at the same time, each of these 4-bit blocks, okay? And then their carry look-ahead logic right here is dealing with if there's a propagate term, it's called, or a generate term. And it deals with it for every set, and then finally determines if there's a final carry out. That's pretty cool, because what we can do now is we can basically instantaneously accomplish the addition, which is fundamental to all the operations that we do in the ALU, because as I showed you the picture earlier, set less than is based on the addition, branch equals based on the addition, the subtraction, and then we can do multiplication through shifting and other things. So this is a pretty big speed up the common case, right? There's always going to be addition occurring. I mean, that's fundamental to computer assembly and organization. And so building a carry look-ahead unit allows that addition to take place simultaneously without having to do a ripple like I taught you guys about here, where we just slowly carry the 1 bit at a time. Instead, a carry ahead unit deals with each of these functions by creating Boolean arithmetic for each of the carries. I'm not going to spend a lot of time on this. The book does a really good job talking through this and how a carry ahead unit, carry look ahead unit, is built, again, based on creating a table, based on creating arithmetic from that Boolean arithmetic from that table, and then turning it into a circuit. we talked about here the improvement in performance we can get by doing this. I mentioned that. Okay, let's talk about clocks now in more depth. So a previous presentation for kind of cursory review of Appendix B, I just talked about how there's right here, propagation time, excuse me, I need to find it right there, propagation time for storing information, and the combinational logic, and then the setup, and so we create a clock cycle based off that. Well, why? Let's go a little deeper into that. Here's why. Because we have states, right? So up until now, we have spent about 90% of the time in the last lesson and most of this lesson so far focusing on sequential logic. So, combinational logic. And so there were no stored states. Data was presumed to be immediately available as it went through its logic data path. Well, obviously, we use registers. Well, registers, and this is kind of using VHDL and Verilog and the common accepted practices of representation, are stated here as a register file. Okay, and a register file, the schematic here drawn out, right? And this is a 5 value because you have 1, 2, 3, 4, 5 inputs and 2 outputs. So kind of 5 to 2, but another conversation. So the register file is important, and the book does a better job. I'm going to switch to the book here. Talking through how we create a register file. So a register file is a combination of latches that build up to make flip-flops, and it's a way to store data right here. So here's a cross-coupled NOR gates that store an internal value. So basically they're cross-coupled so the value is retained. This is most fundamental, but what we use for this class and commonly is right here, a latch implementation, which has a value D, a clock input, so the value, the input value, and the clock cycle. So these are sequential logic by definition because they depend on the clock cycle and on a current input. Okay, but they also have the previous state stored in them, which is the output Q. Q naught is available also, but Q represents the output value. So putting this all together, what it looks like, what you often see is, I thought they had a good, right here. You can stack these flip-flops, right, and create registers. So register 0, register 1, register so on, up until, let's say, register 32, okay? And then we can use some combinational logic or a decoder as a mux to determine which to read out of this, because all we have to send in is the address, right, of the flip-flop we're interested in, the memory location, okay? And then we also have to send in a clock cycle. When we send in these two things, what comes out is the read data. So that's how we build the logic for a register file for the read portion. The write portion is very similar, except what do we need? Well, we need to know the address again, so we'll have some decoder with the address. And this is similar to what the example I showed in the previous video with ROM, right? How we do the decoding with combinational logic. And then we have an AND here, our AND plane, right, for writing. And so we're going to send in the location to write, the value to write, and then missing one more piece here, which I think it shows in the slideshow, and then the select write. Okay, so that's the part we're missing. So we put in the write register, the write data, and then select write. Okay, so that's where register files come from. yeah, it doesn't show everything. Well, here it says right. Here's the data. I guess these are inverted compared to this. But anyways, so here's the value. I apologize earlier. I said this was the, here's the selector, okay, enabling it. So you can see though the register data goes to the D of each flip-flop. These are just the flip-flops I introduced here from the book a second ago, right? The write comes in on the clock cycle, right? That's enabled, and the value comes in on the register data. Okay, well, again, this all kind of bootstraps. You can take one of these, put these together in an array, and now you're building RAM, right? The slideshow here in the book talk both SRAM and DRAM. The slideshow briefly talks about SRAM. I'm just going to mention it here. It's a whole nother conversation. DRAM could be probably another class, but I'm not going to talk a lot about DRAM. So that's how we put together using sequential logic. That's why this is under clocks. Register files or a register, and can build that together to build RAM. Okay, so now in these two presentations of Appendix B, you ought to be familiar with and understand the basic building blocks of circuits for combinational logic and sequential logic. So that gives you, I mean, you can build a full ALU out of that, and you can see where that all comes together in this image. I apologize for jumping around. Right here, because we have both. Right, we're reading memory, so sequential logic, right? Register. We have a register here, right? And then we have a whole ton of combinational logic going on. So that kind of brings it all together. I'm kind of wrapping up, but we do need to talk about clock methodology here a little bit, because there are some interesting things that go on with clocks to wrap everything up with what's called finite state machines. Finite state machines basically are the way to express all of this, putting it all together, right? Where we have both combinational and sequential logic, and they depend on previous state and current state. And here are different definitions: a Moore machine, Mealy machine, to describe the state change depending on the current state versus state and an input. Okay. These are again ways to discuss logic, right? Similar to truth tables and the way we could simplify an and or plane, they came up with a pictorial method to represent finite state machines. So here's the truth table version of it. The book uses, this is kind of confusing, but the book uses an example of a stoplight, right? So you have a green light for north-south, and a green light for east-west direction, and then you have a detector if there's a car on the north-south detector or east-west detector, and they create a truth table out of that. And then again, this is just building logic, but now with a finite state machine, because we need to deal with not just the current state, but current state and an input. So the current state of what it is, right? And then the inputs, and then what the next state will be. So, putting this all together, I mean, this is kind of, you gotta have, this builds on everything we've talked about so far. In a finite state machine, representing this as a truth table, okay? If your current state is north-south, light is green, and your inputs are 0, 0, so there's no car on the north-south or east-west, the next state is north-south light stays green. If your north-south light current state is green and your north-south car input is 0, and your east-west car input is 1, then the next state is, well, we need to turn the east-west green light on and shut off the north-south green light. So this assumes one state, okay? It's either north-south green lights on or east-west green lights on, and presumes that there's a red light on the opposing when the other is green. So in plain speak, right, if there's a green light on north-south lanes and a car arrives sitting at the east-west lanes, hopefully the east-west light changes to green soon. Alright? And then this deals with all the possible states. Hopefully you don't have any don't cares in this. Maybe that's why I get stuck in traffic. Maybe someone put some don't cares in their stoplight calculations. It's like the stoplights when you enter the freeway and the ramps. It doesn't care if there's a car waiting or not. It's just, there's no state. It's not finite state machine, right? It just cycles. It's sequential. Versus at a four-way intersection here, clearly you have to have some state logic. This is one example of it, demonstrating how you can, a finite state machine implementation is going to exist of both combinational and state logic. Okay, and you can see right here that the inputs are available on a clock cycle. That now, because of this right here, this controls that all of this now becomes dependent on clock cycles. Okay. All right. Now this goes backwards a little bit, but this like kind of zooms in on this big picture perspective. I know we're bouncing all over the place. Maybe in the future I can update these presentations, but zooming in right to like a single path here of a single bit, okay, through this finite state machine implementation. Here we go. We have a single flip-flop register. We have a clock cycle input. We have the data input. We have the output. We have some combinational logic block. So this isn't refined here. Pardon me. We have the combinational block output, which goes into, so this is perhaps a read, the combinational block arithmetic, and a write. And I talked a little bit about this before. Now, getting a little deeper in this second look at this. This presumes that all the paths of the wires to these different locations of logic are the same. So your total clock cycle is going to equal the total time it takes to go from the beginning of this data path to the end. There's one problem with that, clock skew. That the clock pulse arrives at different components at different times. Well, why? Because this is nice and pretty the way this is drawn, but what if you have a system where these have different wires, right? The clock here, the path from here to the clock input here is 1 nanosecond, but the path from here to the clock input is 2 nanoseconds. So this, which would, I mean, this is a drastic example I just spoke of. That would be a lot of wiring. But just hypothetically, then you get skew, because even though the clock is consistent, and let's say it's a synchronous system, so it depends on the clock, when that edge arrives, either rising or, in this case it's rising for both of these, or falling, are going to be at different times because you have different lengths of wires. Well, that's kind of a bummer. So that's called clock skew. So we have to address that, and right here it says clock cycle time must account for skew so that variation in pulse arrival do not affect values read from devices. So what we do is, it doesn't show it here well, trying to find a good example. Yeah, it doesn't show it here well, but the book does a good job. We just add an additional component here called skew. Let me see if I can find that briefly. We're doing fairly well on time on this presentation. Right here. So here's your delta, your difference, right, due to the clock skew. So you just, and it has a better picture. Thought it had a better picture, but there, right there. So now you deal with the propagation through the state or sequential logic, propagation through combinational logic, any additional setup, and the skew. That's what you really ought to build your clock cycle off of. And we talked about in class, the longest path, right, through your LU theoretically is going to be the clock cycle. Lots of assumptions in that, but as an example. One thing worth mentioning here is metastability. So it's kind of like a Star Trek sounding term, but if you're not careful, what can happen is you can create metastability. So basically, you're well, there's race conditions and metastability, but metastability is the case where you're reading and writing at incorrect times, essentially. So your input values may not be there yet, or your clock value may be at an intermediate value. In all these pictures, we always show this nice, pretty, it's there, bam, instantaneously. In real life, right, there's what's called rise time, so it's kind of like a sinusoidal wave, and fall time. Okay, so this isn't real, but depending on what your time segment is, it may be a realistic perspective. So you need to be careful if you hit this during its rise from 0 to 1, and we start the clock cycle right in between, you can have a metastability situation. So you kind of send a half voltage into your clock input. I think we talk about race conditions here. Yeah. So race condition we've talked a little bit about in class, but you need to be careful, especially now that we've hopefully you've understood a little bit of how, since in hardware we can create truly parallel data paths, it's possible to have a really horrible race condition where you have a data dependent value or action that you're supposed to perform, and we talked about this previously, so I won't spend a lot of time on it, but basically it's supposed to wait on another value, and you didn't build the logic that it waits, and so in one, like a multiplication occurs, or we'll just do a simple A and B occurs, and then it's supposed to be the result of that and C. Well, since you can, let's say with a programmable logic device, have all of these running in parallel, A may be ANDed with B at the same time as C starts to AND with the output of A and B, even though the data hasn't completed its path through the A and B yet. So it starts reading from C and performing an AND with C and the supposed result. So that's a race condition. One of the ways you can avoid this and create some better metastability is you can have two-phase clocking. So you can have two synchronous or two phases of clocks. So they're in different phases. So phase 1 and phase 2 here of the two different clocks. Fewer race conditions, more sensitive to skew. In other words, there's more opportunities for skew, I think, because you have this rise and fall and this rise and fall. But it's somewhat of a safety mechanism for better control timing of complex logic. Big picture, real quick here, asynchronous versus synchronous. Synchronous depends on the clock. Asynchronous doesn't depend on the clock. Okay, I'm not going to spend a lot of time on that. Finally, I've mentioned this throughout a few places, but there's some really cool devices out there. This is another reason why, given our time constraint in this class, I still wanted to go through Appendix B, because in the industry I have done some programming with field programmable gateway arrays and with VHDL and Verilog, and so you may find yourself doing this, at least in this time, current time. It's fiscally worth it because there aren't that many doing it, and most companies sure appreciate it when you can build a somewhat semi-custom circuit for them using an FPGA. And you can parallelize operations that are traditionally done in a sequential method using a field programmable gateway array, because you can highly customize it to the specific application. Now the trade-off to that is, now that you've built it specific to the application, I ought to have some examples here, but I'll keep it short for time. If you build it specific to the application, obviously, then you're introducing maintenance, updating, and obsolescence. So there's some trade-offs, but overall there is some really cool stuff with field programmable gateway arrays, because this is basically building logic circuits on the fly using Verilog and VHDL as your expression language. Alright, that's it for Appendix B. So in summary of the second part, we more fully fleshed out what are don't cares, and how truth tables and all this programmable logic array applies to MIPS. We talked through right here. How does it apply? And we talked through the opcodes and the paths that it takes in the CPU control data path here, right? And its control unit. Okay. We also filled in some of the specifics on VHDL and Verilog, and on explaining synonymous terms here: blocking, non-blocking, or in other words, data dependent and or asynchronous or simultaneous occurring operations. We touched on an adder again to explain what a ripple adder is versus a carry look-ahead adder. So it adds this unit, so things can be done simultaneous. We also talked through here how we get the equal 0 and set less than value, and I used the book to talk through that a little bit. We talked through then we transitioned from combinational to sequential logic. I used the book and the slideshow here to demonstrate what a flip-flop is based on a latch, how we use these flip-flops to create registers, or what they refer to as a register file, and however many bits you want that long. Then we talked about how we read from them, how we write to them, and what that looks like symbolically. Here it's this whole thing plus the read portion simplified into this schematic. Then we touched on RAM, both SRAM, mentioned you can read on your own on DRAM. Talked very briefly on finite state machines, because this is just the nomenclature for describing everything we've been doing so far, putting it all together. The book gives the example of the stoplight four-way intersection. We went through 1-bit path of this finite state machine hypothetical example. And then finally I closed us up with clocks and clocking methodology, and then talked about somewhat of the so what, why is this useful in industry. It's very financially worth it right now if you find a job doing Verilog or VHDL programming, and this will really help you understand what's going on when you're using your high-level language and doing assignments.